I'm Ben, this is Jason. The genesis of this talk was I was fishing around in January when the call for papers went out for C++ Now, and I didn't have much idea, and I messaged Jason and I said, do you want to do a collaboration? And he said, sure. What on? I said, I don't know. He said, well, I've got this title. It's constexpr all the things. I'm like, that sounds great. So obviously, if you don't know this meme, it's from Ali Brosh's excellent Hyperbole and a Half webcomic and book, and we co-opted it. So this is Jason Turner. He doesn't need much of an introduction, I'm sure, to many of you. He is a trainer and contractor working out of Denver. He is also the co-host with Rob Irving of CPP Cast, and also the host of C++ Weekly, which just passed its year mark, and CPCast just passed its 100th episode.
Yep.
And somehow, in between all that, he finds time to usually submit multiple talks to multiple conferences throughout the year.
Well, it helps when you don't have a regular full-time job. So this is Ben Dean. He is a principal software engineer at Blizzard on the Battle.net team, and Ben likes functional programming, and a lot of his talks have been casually related to functional programming in some way or another. He's a regular speaker and attender at C++ conferences also. And
that's a polite way of saying I get all my ideas from Haskell. So in the interest of not bearing the lead, we want to start out with kind of the proof of concept. When I first heard about constexpr and I heard about user-defined literals, I immediately thought, is this possible? Can we embed JSON literals in C++? Because JSON's ubiquitous, JSON's kind of useful, it's not too difficult, it's well understood, the grammar's well understood. It's also sufficiently interesting because it's fundamentally recursive, so there's some interesting problems to solve. And it's kind of, to me, this is kind of a bellwether for what's possible with constexpr. If this is possible, many, many things are possible. And if this can be made easier, many, many things get easier, I think.
So the promise of constexpr, what we're hoping to get out of this is better runtime efficiency. If you're calculating stuff at compile time, it's less to do at runtime, pretty straightforward. Clear code, fewer magic numbers. This is an interesting thing that I think we'll dig into for some of the options for what we mean by fewer magic numbers, and less cross-platform pain. So as Ben pointed out, we're trying to lead towards this goal of being able to do a JSON parser at compile time, and that eliminates the need to have an external tool that's generating C++ code for us from our assets.
Mm-hmm. And if you're working in a cross-platform environment, deleting a step from your build chain is kind of a big win. All right, so in putting together this talk, I kind of thought, how do we get here? So, a constexpr history 101. It struck me that there are kind of three ages of constexpr. So the first age was kind of extreme recursion. We were only allowed one return expression per function in C++11. We started to see constexpr math functions. Scott Shore gave a couple of great talks here and at CPPCon, and discovered things like the throw trick, where so the trick there is, if you have a constexpr function, you're not always sure whether it's being evaluated or whether, you might take the result of that and forget to put it in a constexpr context. So you might assign it to a non-constexpr variable, and then the compiler would emit your function when you didn't mean it to. And so the throw trick was discovered, which is that you declare a symbol, but you don't define it, and then you put a line of code in the constexpr function, which doesn't get evaluated normally when you call it constexpr-wise. So think of it like a square root function, and if you pass it a negative number, obviously it's undefined. So you would throw, but you would throw an undefined symbol, and you effectively turn what would be accidental emission of the function into a link error. So we saw things like this in the first age, and that was cool. And the ages seem to be, to me, characterized by what kind of string hashing you can do. So the mainstream discovered constexpr string hashing, and I'm sorry, my comments are really lost here. But basically, in the first stage, we had the fall of Gondolin, some Balrogs destroyed, Morgoth defeated, and then constexpr string hashing discovered. So at this point, most people are probably familiar with this or something like it. This has been, this kind of thing has been widely sort of brought into the constexpr mainstream consciousness. So the second age, we saw things like generalized constexpr being supported by Visual Studio, which is cool. A lot of more general sort of compile time computation and optimization, things becoming constexpr, and that's been popularized by things like C++ Weekly that Jason does.
I did not put that line in the presentation, just for the record.
And of course, generalized constexpr string hashing, like MoMA3 has been discovered, and constexpr libraries starting to appear, I think. So the end of the second age looks something like this. Like I said, the MoMA hash. The mainstream consciousness seems to me to be following what string hashing is available. So I think now we're at the dawn of the third age with C++ 17. And that means a lot of cool things. Constexpr lambdas, which as we'll see, are very powerful. We've got if constexpr, which is kind of changing up how we do things like enable if and template specializations. And we've got, at the moment, an interesting selection of constexpr things in the STL. So things are starting to be born into constexpr land, things like string view. We've got constexpr coming into things like array, almost all of chrono. And very soon, I expect we'll have constexpr cryptographic hashes. Is it still me now?
I think so.
Okay. So one of the problems with constexpr is this inability to write a function and control or even detect whether it's being used in a constexpr context or not. And Sean Middleditch, put this comment on Reddit a couple of months ago now. Basically, the problem is that when you're working in constexpr, you naturally have fewer tools than you do in runtime, and so the kind of algorithms you use to solve problems at compile time aren't necessarily as efficient as the ones you would want to use to solve the problems at runtime. And so but you can't tell which context you're being evaluated in when you're in a constexpr function. So what you would like is something like this. Imagine we have a function template that does a hash. When we call it constexpr, we want it to use our constexpr version, which is this kind of maybe linear recursive thing. It's not something we would choose to do at runtime. And when we do it at runtime, we like the using all the efficiency features that we can bring to bear. So there's still not really a very good story for this, but you can do, if you're really determined, things like this. You can try constexpr Sphene, and this is using something like the new detection idiom. So this is the thing you would feed to the detection idiom. So if the T here is constexpr constructible, it's admissible as a compile time argument to the comma operator on the end there. And so the result here is going to be a well-formed template argument. And in that sense, the use of the comma operator here is similar to void T. So void T turns any type into void. The comma operator here turns any value into true. And Marshall is
wants to plug his talk on Friday about the detection idiom.
Right. In fact, I rewrote this slide after I watched your talk on YouTube, Marshall. So yes, Marshall's giving a talk about the detection idiom on Friday, and it's really good. So we can write something like this, and then we can feed it to the detection idiom, and we can have code like this that basically says, call the constexpr function if you can. Now, the problem with this, as you probably are aware, is that there are many caveats. Firstly, constexpr constructible doesn't mean constexpr hashable, right? This wasn't quite what we wanted. Maybe we could get around that with a better expression. Maybe not. But the bigger problem with this is that, in fact, constexpr capable doesn't necessarily mean it's being called in a constexpr context. And that's the thing you can't really detect right now. But nevertheless, I mean, and you've got some verbosity and maybe some compile time issues. Those are probably less worrisome. But if you're going with this kind of thing, it might mean, in the limit, separating all your types, one set for compile time and one set for runtime, and having some hopefully cheap conversion at runtime for when your compile time things come out into your runtime. But in our opinion, the better solution to this is a current proposal from David, which is a constexpr operator, which exactly solves the problem of how do I know if I'm in a constexpr context. And that would allow you to properly write, functions that use all the compile time efficiency you want, but if you're in a constexpr context, you just use the tools you have and get the job done correctly, and that would work.
So this is what we started with. We want to do some sort of constexpr compile time parsing of our JSON. And we have two issues. The first is how to represent JSON values in a constexpr capable way, which I'll be talking about next, and then we'll lead into how to actually parse these JSON values. So a JSON value is a discriminated union of null, boolean, a number, a string, an array of values, and an object, which is a map of string to value. So clearly we're going to need some sort of recursion because we're going to have objects that can contain objects and maps that can contain objects and strings and etc. And we're going to need constexpr ways to deal with string, vector, and map. So we're going to see where we can get with that. So for constexpr strings, C++17 adds standard string view, and it's great. But like a lot of C++17 things, the exact status of it depends on your current standard library implementation. And string view, it's kind of in the name, is really only intended for viewing strings. It's not intended for storing strings. And I've seen some articles lately about, if you were to put data that was on the stack into a string view and then keep a handle to the string view, and now you're accessing things that have popped off the stack. This is entirely possible. So this is string views. Well, that's not really what we want there. So we need a way to pass and store in general, work with character literals, and string view, it mixes metaphors. We don't want to be using something that's called string view if we're actually holding or manipulating strings. So our first thing that we created was this static string class. So, knock over random bottles of water around here. This, the first constructor uses the ability to determine that you're actually working with a const char array. So a const char array, or a string literal specifically, is guaranteed to live for the lifetime of the program. So this, I'm sure, can be abused because you could create a const char array locally on the stack and then a char array locally on the stack, pass it to this. But the idea is that we're trying to detect that you're actually working with a string that we know the lifetime of on the first constructor, and it deduces the size of it. And then the second constructor gives us a way to look at a subset of the string. And this is pretty straightforward, a constexpr default constructor, and our size C string data pointers. Anyone have any questions on this? All right.
So, sorry, is it different from string view in terms of what does it bring to the table that string view does?
My microphone is static. What does it bring to the table that string view does not? And primarily this first constructor, so that it's easy to construct it from a const char literal. And Marshall has a comment.
You have the SV suffix now.
Right. Yes. So we could have used the underscore SV suffix, and we do actually use that in the implementation of these things.
It's not underscore.
Yeah.
Oh, it's just
It's
SV. Sorry.
standardized, so it's just SD.
Okay.
And you will see that later.
Okay.
But
Right.
it's in the namespace.
Yeah, I know.
So it's more of a semantic question because we want to pass these around and store them and have some degree of confidence that we're doing something reasonable doing that. So then that leads us from string to vector. And we have our, there's an implied namespace here, by the way. All these are in our CX, constexpr namespace.
Right. In later slides, if you see something CX qualified, that's what that is.
Right. So it's constexpr. We cannot allocate memory, so we must know ahead of time approximately how big we want this array to be. So in this case, we have a default value of 5, which is small, but we'll get into in a minute why that size was chosen for these earlier examples. So it's just an array that is default initialized because everything in constexpr must be initialized. So I had to, fill this with whatever it's got, and the size is equal to 0. That's reasonable. Yes?
Maybe you have that later, but it's worth to mention David's proposal for a constexpr vector.
Yes, we will mention that later.
Right.
So we don't need to get it on the microphone yet. No. So we just need to implement our iterator's pushback. That's the comments that you can't read here. The pushback and operator, index operator, but we'll get there. So our begin and end, constexpr, that's easy. Pushback. So, all right. I like audience participation. Why would I be... let's talk about this throw here. Does anyone have a problem with the fact that I'm throwing in a constexpr function?
It just won't compile.
It won't compile if you get too big.
Right.
And that's the idea. But it also wouldn't compile if you got past the end in a constexpr context either. Yes, Louis?
It is going to compile unless you... it's going to compile if you're going to do that at runtime, right?
Right.
It's at runtime, unless you force it in a constant expression. But since you're returning void, it's untruthfully aren't doing that. I mean, you probably can do it, but...
No, yeah, this definitely all works. So so the basic concept is each time we push something back, it increments the size, and that's fine. And then if we get past the size, now, if I did not have this throw in it, and you're using it in a constexpr context, and you get beyond the maximum size, you're going to get a compile time error, because it's going to say that you're accessing past the end of an array. By adding the throw to it, I give us something that can be used safely in a runtime context or in a compile time constexpr context. Make sense? So,
Do you also get a better
hey, there's
error
Tony.
message in the compiler?
Do you get a better error message? I don't.
Do you see index and the vector show up?
I don't recall. Do you?
I don't remember either.
I think it says you did a non-constexpr no you threw.
Yes, and I think it would show the line and the content of the line.
Yeah. So
Right.
it's a message there somewhere.
Yeah.
So notice on the bottom here, we're not able to use next here, and that seems to be a bug in our implementation. So for all these, the unspoken thing here is we're using GCC for all of this.
Right. GCC 7.
Yes.
I think the latest one I used was April 20th.
I don't remember when I last compiled, but really bleeding edge. Clang has been hit or miss. We got it almost all the way compiling with Clang. Partially it's standard library issues.
We'll cover stuff as we go.
Yeah. So, hey, it showed up.
It's loaded there. It's just not loaded there.
That's great. So we can see in the compiler explorer here that the iterator category is not constexpr constructible in GCC's internal implementation. So we can't use standard next, even though we'd really like to. So I'm just doing iterator pointer math, but it's fine.
Did you report the bug?
No. I am reluctant to report bugs on things that are changing every day, honestly. But I didn't also...
I didn't report any bugs we found.
No. Maybe we should go back and do that.
It's rather a class of bugs than one single bug. But,
so this gives us, our vector can now look like a standard library, a standard vector pretty much. And so, I mean, you just push back into it. Yay. And in a constexpr context, now we can do a static assert. We can do a compile time check, say, hey, look, we have a vector of size 1. That's what we were expecting, and it works. So from here, we build mutable constexpr strings. So we are doing that simply by inheriting from vector. And so our concept of basic string takes the card type and takes the size and passes that to our vector base class. And then we have a couple of constructors to build from our static string that we mentioned earlier and from standard string view. This does play a couple tricks. Bullet points, constexpr data numbers must be initialized. That means we know that all of the data in our string is equal to 0. So that gives us implicitly a null terminator on our strings. A little bit of a cheat. And I have not yet provided any methods for shrinking the data structure, but all you'd have to do is set that last terminating 0, and it should be good. So carrying on from there, map is kind of obvious. It's just an array of pairs of keys and values. Although I guess to call this map is not 100% correct. You came up with a good name for it. It's I think you did.
It is a flat map.
It's a flat map, but it's also a flat unordered map. And
something like that. Yes.
Depending on what you did, you might even get multi-map. It's not very well constrained at the moment. But
CX pair.
Yes, and the CX pair, which we'll get to in a couple of slides. But yeah, so we're using our own implementation of pair. That's important. We'll show why in a minute.
It's very minimal, but
extremely minimal.
Yeah.
Actually, we don't even show the implementation of pair, but we explain why we needed it. So building on this, we can just make our index operator, do a find to see if the thing's there. If it's not, insert it, and then you can use compile time maps like this. So I'm going to have to, well, on the, so we're doing a constexpr auto colors equals get colors. So we're just getting a thing that's populated with a map of colors. And the one that's returning red, we get returns OXFF0000 because that's what we populated with at the top. And the one that says colors blue is a compile time error. And Richard does or not like that for some reason. Why do we get a compile time error? Because it's a constexpr thing and we did not populate the value blue. So
right. The find inside our map is failing.
It's not going to return default value?
No, we can't because it's constant. So it would have to initialize it would have to populate the member of the map for that value if it were to keep with normal map semantics, and it can't. So it's a compile time error. And there's like a discussion about magic values. I could argue that this is better than using an enum. If I wanted to. Does anyone want to argue with me on it? I'm looking for some. You want to argue?
Can you confirm that there's absolutely no runtime cost associated with that? Because the colors, so in the int main, colors bracket red and bracket blue are not in a constant expression. Therefore, it's implementation. It's a quality of implementation whether there's anything on there. And so I hear you laughing, but check the assembly.
True. This slide, I take responsibility for all slide errors.
No, I don't know if I agree, though, because you will definitely get a compile time error on the blue version, no? Wouldn't you?
I'm not sure.
Yeah, but
I thought I ran it. Now I'm wondering.
I think the observation is that unless you assign the result of colors red to a constexpr variable, it's not going to be in the constexpr context necessarily. So.
Yeah, that's what I'm saying. That's exactly what I'm saying. Therefore, you don't know whether there's any code generated for that.
Right. I guess it's
right.
possible.
It's
Oh, yes,
problem.
right. We would have to. Yes. Okay. You're right. Sorry.
constexpr auto.
Yes.
Yeah.
When that would, yes, we'd have to, you have to, and that's a continuing theme that we don't mention specifically, but actually testing constexpr data structures takes discipline.
Yes, I would say.
So, are you going to
I
risk
think
it?
I can. It's just, let's try it. This is an embedded Compiler Explorer view.
Yes.
that's
So if
why
you
I'm-
didn't know, Compiler Explorer supports embedded HTML views. So why did we have to make our own pair? This is why. Because pair's assignment operator is not constexpr. It is the only part of pair that is not defined as constexpr, and I cannot think of any reason why it's not. The only thing I can come up with is perhaps the people that were doing an audit of constexpr things in the library said, well, it's constexpr. Why would you need to reassign it? But you do need to reassign it.
Did you submit a library issue?
No, but I'm building in my mind the things, because it goes beyond constexpr, the things that are coming up in my head and the more time I spend with this. And we should probably do that.
Yeah, we should. We'll make a pass.
Yes, it's we'll But it's more fun to reveal it live in a talk.
You guys don't get it. It's not an either or thing. Embrace the healing power of and.
And yes, right. So, but we have to present this first, and then we can submit the library.
This is our motivation.
Yes.
I hope that still works.
Yes.
All right.
Now we have to submit it. Okay, this constexpr find if. Looking at this implementation, does anyone see how it differs from the idiomatic version of find if? Anyone? Okay, I'll tell you.
Curly braces.
What's that? It has extra curly braces, is that what you said?
Yes.
Marshall. Okay, how it differs is we added the keyword constexpr right before the return time.
I think this isn't working now.
Oh.
So I can try and reopen our notes. I'm going to try it.
Minor technical difficulties, excuse us. So, yes, and that leads us to Bryce.
Yes. We watched the Twitters.
Bryce said, reviewing code I wrote last week, I found 3 implementations of constexpr transform. Constexpr algorithms, please. Many of them, you just need to add constexpr to the beginning of it, and it's now a constexpr algorithm.
And I can see at least several people who are in this room have liked that.
Yes.
Possibly.
Yeah, that's probably, oh, if you're gonna... Oh, hey, there's Vittorio. Recognize that one. Oh, and you. All right, yeah. Okay, so other algorithms that we had to do basically the same thing too. And I don't know about you. You implemented some of them. And the ones that I implemented, I literally copied the CPP reference version and added constexpr to the front of it.
That's what find if was.
Okay.
That's what all these were too. Yes, library in a week.
We're still open for suggestions.
So, well, anyhow, those are the things that we had to do. So that brings us to, I think I might be moving a little slowly. That brings us to how do we actually represent our JSON value? And I have to admit 100% that I completely lacked the imagination for how to do this, and Ben pointed me in the right direction for revision 1. Ben gets into much better revisions. So we have our JSON value. Notice the template parameter depth equals 5 at the top. Yes, Bryce.
Before we get too far away from algorithms, my answer to the can we have context-with parallel algorithms remains no.
Bryce says we cannot have constexpr parallel algorithms. I think he's wimping out here personally. But
Bryce?
we constexpr all the things, Bryce. So we have a struct. So notice the depth equals 5 on the top line. And we have our struct data. Now, this should be a union, not a struct here. It was a struct because of a misunderstanding between me and the compiler. But in the version that's up on GitHub right now, it's a union. So we have our data and our possibilities, our bool, our number, our string, our array, and our object. And notice the depth -1 for each of these vector and map implementations. This is how we're building our tree. So it's a tree that starts with a max depth of 5 and works its way down. So it's a tree that expands by our max vector size and max map size are 6 and 6 each. So each layer could have 6 vector elements or 6 map elements in it, 5 deep. And what do you calculate? That's 7,000 something.
Just less than 8,000.
8,000 template instantiations.
8,000 instances. I don't know if it's template instantiations, but
Well, I think it had to.
this is the first thing we thought of that could work.
Right.
I think that's the way to put it.
Oh, and actually it'd be like 8,000 times 3 because it's the maps and the vectors and the values and the, well, anyhow. And then the terminating 0 at the bottom so that we don't continue to go any further. And then we just treat this like a JSON object. We have a toArray method. The const version of it asserts that it is currently an array. If it is not, then it throws. And in a constexpr context, we have a compile time error. Yes, Bryce.
Seems like you want a constexpr std variant. Why don't you just have that instead of...
A constexpr std variant?
Yeah.
I'll tell you why in a few minutes. So, And then our non-const version coerces the type into an array just as it would in the world of JSON things and returns the value. And then we can do things like this in a constexpr context, and they work. We can index into objects, we can set things, and we can push values in.
And you can imagine, so we showed to array, but we have to string, to number, to object. And indexing does the to object implicitly.
Right. So why not std variant, Bryce? Similarly to standard pair and variant, it's missing a few key constexpr things. Notably, it does not have a constexpr copy constructor, does not have a constexpr move constructor, copy assignment, or move assignment. And those were all necessary. Well, at least 2 of those were necessary to get this to compile. We need assignment and copy, at least, I believe. So it's as far as I can tell, there's no reason why in the library it couldn't just be made constexpr. Yes.
So to implement variant, you need actually you're going to have heard that. You need to in-place moves and stuff, right? Sometimes or all the times. If it's not trivial, then not. Okay.
So if it's not trivial, then you must in-place new it, which is why we can't do constexpr in these cases.
Right.
Right.
Okay.
And also, what you're going to say probably is, but why can't we have in-place new in the constexpr context? And that opens a huge gap.
Yes. So yes, I won't get into the why cannot we have in-place new in a constexpr context. I'm not involved in this discussion.
So treat these as empirical observations, I guess, and we can argue about all the implications.
My only point is there's a very good reason why those cannot be in a constant expression right now.
Right. There's a reason they can't be. Yeah. Go ahead. Yes.
Be conditionally constexpr.
Right. Yeah.
Well, yes. Yeah. Right.
So did you say these examples were all from GCC? Is that what?
Yes.
Okay.
Yep.
Okay. All right. So, what things can we store in our containers? What are basically the requirements for our compile time things? They must have at least one constexpr constructor, and they must be trivially destructible. Nothing else is required, assuming it does not get invoked in a constexpr context. So we found these shortcomings in array. Well, array is an implementation thing. Some of the standard library implementations, depending on which compiler you're using, may or may not have full array support. String obviously is not constexpr, but there are versions of it that could be. String view, we found corner cases where it didn't do quite what we went to. Pair and optional and variant are the things that we just talked about without being able to do assignment. And standard swap is not constexpr anywhere, and I might get an argument here, but I'm 99% sure that it could be. I can't imagine why it couldn't be constexpr. No one's arguing with me. So standard swap can be constexpr. We'll submit that.
But what's the interesting part here is that some of these things were born into the constexpr world, like string view, and string view does the best job of any of these things of being constexpr. Yes. But there are still a few implementation issues that we find here and there.
So our containers have a fixed maximum size. They currently cannot shrink, but that could be done. And they require types that are default constructible. Because you saw that I have to initialize the array of things. I posit the idea that we could wrap all of the things inside our arrays as standard optional, and then we wouldn't require them to be default constructible. We could just emplace them with the construction that we wanted. I didn't actually try that yet. And it should be possible to templatize on constexpr-enabled allocators, making all of these things optionally constexpr. Does anyone... Everyone's okay with that, okay.
Allocator, you need constexpr placement new, and that is available.
Yeah.
So you need constexpr placement new. This is the thing that I was overlooking in all these conversations, is the constexpr placement new issue, I guess.
Yeah, because that's how allocators construct things, is placement new.
Right. But if it were one that was intended only for constexpr allocation, it would not need to use placement new. It could default construct the array of things inside it, like on this slide, and then simply reassign those things as it needed to and keep a free list with... I believe that you could implement an allocator that is intended for types that can be used in constexpr context. And Hopefully I didn't move too slowly.
I think you bowed out quickly to avoid more arguments.
I'm also looking at the clock, making sure we don't take too long
okay.
here.
All right, so that's kind of where we were in our first implementation of actually representing JSON values. So then the part that fell to me was the parsing part. And
The easy part.
yeah, from my point of view, the easier part. So, as you know, I take all my inspiration from Haskell. So, what is a parser? So, there's this great serendipitous phrase: a parser for things is a function from strings to lists of pairs of things in strings. And if Dr. Seuss had been a computer scientist, he would have said this. But actually, Fritz Ruhr, who is a functional programming lecturer at Willamette University, came up with this. But what this means is, and in the coming slides, you'll see I have Haskell type signatures to explain things for those that can read them. For those that can't read them, they're very easy to read, so you'll probably be able to read them in a few slides. So a parser is a thing that takes something like a string and turns it into the thing you want to parse out of it, and the rest of the string, that's the pair. And then the list part is just representing there might be multiple ways we can parse this. Now in C++, we might write a signature something like this. And just an aside on this slide, I've started adopting trailing return type syntax even in template aliases because I think it's really useful.
Yeah, that is not a deduction guide, just for the record, which is what I thought it was when I first looked at it.
Right, that's a function from strings to list of pairs of things in strings. Of course, in C++, we don't really mean lists of pairs of things in strings, or even functions. So when we say strings, we mean any string-like thing. String view, for instance, which will do nicely for a compile-time string. And then, obviously, so the input to the parser is a string view, and the leftover part, when you parse the thing out, is also a string view. And the list here, well, you know, nobody likes lists. Anyway, the list represents optionality, the multiple parsing. We're going to be real simple and just say a parser can either succeed or fail, and we'll replace that with an optional, a constexpr friendly optional type. And of course, when we say function, we mean the usual thing we mean when we say function, anything that's invocable. For instance, a constexpr lambda. So let's have a look at a really simple parser. And I've got a couple of aliases. So parse input t is string view, whenever you see that. And I'm just going to use this parse result t alias to wrap up the pair of the optional, so that doesn't get too wordy. So this thing we give it the parse input and the char, and it will either match the char or fail. So very simply, looks at the string view. If it's empty, we obviously fail, or if the thing doesn't match, we fail, and that's returning null opt. Otherwise, we return the result, which is the char we matched and the rest of the string literal. So that you can see the data plus 1 and the size minus 1 is kind of giving us the rest of the string view there. So that's really simple. That will match a character that we give it and a string view that we give it. Now, if you've been paying attention, you'll realize this isn't actually a parser yet, because that's the wrong type signature. The comment says Cecine parsing parser, but you can't see it. So it's not quite a parser because it doesn't take only a string view. It has the wrong signature. The signature is what we said before. But given that we have constexpr lambdas, we can write a function that returns a parser, which is itself a constexpr lambda. And here it is. This is exactly, the body of this is exactly what you saw before, except we've wrapped it up in the lambda, which is the actual parser. And the make char parser function obviously takes the char, captures it in the lambda. The lambda is then our parser for that character. Yes? Easy, right? Well, now, that's the simplest parser we could make. Let's move on to some other parsers. So parsing fundamentally works on string-like things, so it's going to be useful to write something like this. We can only match one char so far. What if we wanted to match any one of a number of chars? We might write something like this, and I call it one of. So we pass it the set of characters that we want to match, any one of that set. And what it returns us is, again, a parser, which is a lambda of this type signature. And it's just doing the kind of obvious thing. It's saying, take the first character in the string view you give me. I'm going to look for it in my set, and if I find it, I succeed and I parse that character. But if I don't find it, I fail and I return null opt. Happy? All right. Well, now we have one of. You can imagine very, very similarly, if we just negate a predicate in there, we get none of, which is a parser that matches a character which isn't in the set we give it. You can imagine how to write that based on what we saw before. And likewise, we can write a character we can write a parser which exactly matches a string that we give it. So we want to parse an entire string and exactly match that string. We can do that, and the invisible comment says that I used we basically stuck constexpr on the front of stood mismatch to do that. So you give it a string you want to match, it captures that. When you parse, you mismatch that, and you either succeed or fail in the parser. So that's a few primitive parsers. We can parse chars, we can parse one of a number of chars, we can parse strings. In order to build up into being able to parse JSON objects, we need to be able to combine parsers, and to do that, we need parser combinators. So here are a few parser combinators, and if you know a few functional programming patterns, this will start to look very familiar. One thing we want to do is change the result type of a parser. So we've got a parser that parses out a character. We might want to turn that into an int. Well, we can easily write a function that turns a character into an int, and then we want to inject that into our parser, and then when we did have a parser for characters, we now got a parser for ints. And that's fmap, because in the functional pattern speak, that's a functor. A parser is a functor. Likewise, a parser is a monad. We can take the result of one parser, feed it into another parser, and do something based on that. And that's what bind does. Parsers also turn out to be monoids and applicative functors. So I'll get to these in the next couple of slides. But here is fmap. So again, the Haskell type signatures at the top. You give it a function and a parser, and it simply runs that parser. That's this line running the parser. If the parser failed, obviously you can't apply the function to what it returns, so your parser fails. But if it succeeded, all you do is apply the function to what was inside it, wrap that up in your parser return type, and you're done. And the return type is just parse t here is the inverse of parse result t, if you like. It's the way to get the t out of a parser rather than making a parse type out of it. So yeah, the result of running the function on what the parser is going to produce is going to be the result type of the parser that you're going to produce. And you simply do that. All right, so that's fmap. So alternation, the alternation operator bar, is a combinator that you give it two parsers, and it's going to run the first one, and if that fails, run the second one and return the result. If the first one succeeds, it doesn't need to handle the second one. If the second one fails as well, then the whole parser fails. And they have to be of the same type, because what you're returning is the parser of the type, both types that you put in. So that's what we have here. This is just saying, give me two parsers, and they better be the same type. Then what I'm going to do is simply run the first one. If it's good, then I'm all good. Otherwise, return the result of running the second one. So real simple. So this is the monoid operation on parsers, and the unit for the monoid is the parser that always fails. So a parser that always fails, if you alternate it with any other parser, you'll always get the result of the other parser. If you put it in the first place, it fails, you get the result of the second one. Put it in the second place, the first one is run first, so if that fails, it fails. If that doesn't fail, it goes. So this function is just an easy, it returns the parser that always fails, but it returns the thing of the right type that you want.
If I may point out briefly to make sure everyone's catching this, every single one of these is returning a lambda. So this is basically impossible before C++ 17, or extraordinarily difficult.
Extraordinarily difficult, I would say, yeah. It might be possible, but constexpr lambdas really make this whole thing work and actually make it easy, in my opinion. So that's fmap, that's alternation. Alternation turns out to be really useful. The applicative operation on parsers is combining them. So if you look at the type signature at the top here, we give it two parsers, and we give it a function that will combine the results of those parsers into another thing. And what we get out is the parser for the thing that the function produces. And that's what you can see the code doing here. So once again, we run the first parser. And if they both have to succeed, otherwise the function wouldn't have anything to work on. Bryce.
So how would you do that at all before 17? Right, with like a local struct that's
How would you do that before 17?
I don't know.
Yeah, I don't know. You probably by implementing your own lambdas somehow.
Yeah, local callable struct.
The only thing I can think of is the local struct.
Yeah, returning a local struct.
And then returning that by auto.
But this, as you can see, this makes it much fewer lines of code, I imagine. So yeah, combine. I chose to call it combine because I didn't really have a good name for it. But it runs both of the parsers you give it. In particular, it runs the second one on the thing left over from the first one. So it's running them in sequence. Assuming they both succeed, it's going to run the function on both of the results. And then the leftover is the leftover from the second one because you sequenced them. Now, there's a couple of uses of combine that turned out to be really useful. And so I put them under operator overloads. So I used greater than and less than. So these are simply very simple applications of combine, and all they do is run the two parsers and then throw away the right-hand side or the left-hand side. So you keep the thing that is on the greater than side, if you like. And that's what this is doing. This operator less than is just calling combine, and the function to combine the arguments just throws away the left-hand side here. And you can imagine that operator greater than would just throw away the right-hand side. So this turns out to be just really useful. I think I had like not very many uses of combine that weren't one of these. And both of these operators are nice. They're left associative. They're the same precedence. They work really well for building things up. All right. So these are kind of, we're building up things that enable us to build up further. There's a few more things that kind of form a pattern, and that is the pattern of accumulation. Sometimes you want to run a parser multiple times and accumulate the result as you go. And that's what these things do. So you can see from the type signatures, and I'm not going to show you the C++ code, but you can maybe imagine how it works. You get a parser of A's, and this is your seed value in accumulate speak. And then here's your accumulation function, which knows how to fold in parse things into the seed. And what you get out is a parser for the accumulated type, right? So many is a parser that will run something 0 or many times. Many 1 is a combinator that will run a parser at least once, but possibly many times. Exactly n, as you can imagine, runs a parser exactly n times, and so it also has this integer argument, which is the n. And then separated by turns out to be this incredibly useful thing, especially for parsing. You can imagine parsing lists of things. What you're going to be doing is parsing values separated by commas. So it's going to take kind of a main parser and then like the in-between parser. And again, an accumulation style function signature to put things together. And it's going to alternately run the parser for A's and the parser for your separator. And it's going to end up accumulating into your list type or whatever it is you're accumulating. Any questions about this? These are starting to look like building blocks now that we can use to parse real things. All right, so here's a few concrete examples. This parser just eats white space. Really simple. So all we're doing is space or tab or new line or line feed. We're making char parsers for each of those. That was really simple. We're alternating them together so it will match any one. We could have equally used one of. That would do the same thing. And then all we're doing is saying run that parser many times. And I don't care to catch the result, so I'm just using monostate in my accumulation function. So this parser just eats up all the white space that you give it in the string. This parser simply passes a decimal integer, just assuming positive decimal integer. So we can't start an integer with 0, so we start out matching 1 of 1 through 9, and we bind the result of that. So we forward the result of that into the next lambda, And then after that initial digit, we're going to match one of 0 through 9 many times. And we're going to combine them all in the kind of obvious way of shifting and multiplying and adding. Clear? All right. The next one is a very simple string parser. A string is a quote followed by a bunch of things that aren't a quote, followed by a quote. And that's what this is saying. So here's our quote parser. Our string parser says many of not quotes. And all this is doing actually in the accumulation is just taking the sub-string view from the string view you passed it. So it's building that up as you go along. And here you can see the greater than and less than coming into play. This is very nice syntax, so just combining parsers together where you just want to throw away the quotes at either end and return the string.
This doesn't work with escape, correct?
Not yet.
Not yet. Right. We're starting simple. Yes, it doesn't work with escape characters. All right. Okay, so this is what a JSON thing looks like again. So, a reasonable approach to a first cut at this is to use parsers for each individual thing that it could be and just alternate them together. So we're going to have 6 different parsers, each of which parses the thing that a JSON value can be, and we're going to alternate them together.
So if you haven't been paying attention up to this point, this is where Ben proves that he can make magical things happen and anything's possible at constexpr time. So,
all right. Well, it's all in the lambdas. Once I heard of constexpr lambdas, I'm like, this can be done. Yeah. So this wall of text is, as you can see, alternating 6 parsers together, and a couple of them were too complicated to fit on the slide. But then for each parser, it's f-mapping in a function to turn it into the string view given the appropriate thing that was parsed. So either the null or the true or false, or the number, the string, the array parser and object parser we'll get to. And then I decided to take a disciplined approach to dealing with whitespace. So, you could put that skip whitespace parser everywhere, sprinkle it everywhere. It's idempotent. It wouldn't matter if there was no whitespace. But to take a disciplined approach, I decided to put it before values. So anytime you parse a value, it'll eat the whitespace before it and then parse the value and then stop. I said we'd get to these, although they're too much to fit on the slide. But you can imagine now how they work. Now that I've shown you the way that things combine and the separated by combinator in particular. So array parser will parse open square bracket followed by values separated by commas followed by close square bracket. Accumulate that all into a JSON array value. And object parser works the same way, except instead of parsing values, it's parsing key value pairs. So all of this is inside, is this a function template? Yes. These are all function templates at the moment. And so we need a specialization for the base case, which is that last thing which just fails at 0. And given this actually, this works. This is the first cut that we had that actually worked. And so we can write now a constexpr user-defined literal, and all it does is forward the string view that effectively is given into the value parser, and that produces a JSON object, a JSON value. All right, let's talk a little bit. So once we got here, this was kind of proof of concept. Now I started to think about error messages, and the story's not great. Primarily because I have no way to tell the compiler to print out the string. I know where it failed. I just can't get the compiler to tell anyone that. The best I can do is things like this, where I deliberately alternate the failing parser with a throw here, so that I'll get a constexpr problem in the compile, and the compiler will say, "Hey, this isn't constexpr. You made a mistake on this line." And it will. This will be somewhere in the output. Vittorio.
If you don't care about running this a runtime, you might be able to use static assert with a dependent type in order to trigger it only.
Okay, I might be able to use static assert with a dependent type. Apparently.
I think, ironically, you might end up back at the old way that BoostSpirit used to report.
Okay. So BoostSpirit has some tricks for reporting error messages.
Well, hopefully moving forward we can have better ways.
Yeah. There's actually a proposal. There's a proposal.
You would think so.
All right, so what we have now is the simplest proof of concept, right? It works for suitable values, it works. Now, it's a good starting point, but there are some problems we need to address. Problem number one, a JSON number isn't an integer. It's this thing. But we actually have almost all the mechanisms we need to parse this. I found it useful to add just one extra combinator, which is kind of, which I call option, which is for this first optional minus, you can make a combinator which says run this parser, and if it fails, just return the default value. The assumption being default value is plus for implicit positive integers. So this, this is a problem, but this is a solvable problem. This with all the stuff we have. Mikhail said strings aren't string views, and he was perfectly correct. And the problem here is that, in general, the size of the output is not the size of the input. You can't just naively say, oh yeah, I'll take that string view. You have to actually convert characters. And for the Unicode stuff, you'll see that's why I had exactly n, because it's 4 hexadecimal digits. Again, we fundamentally have all the tools to do this. We can output this into a JSON's constexpr string type, and this can be solved with the tools we have. Problem 3 was a little more challenging. And problem 3 was that templates, especially function template, especially recursive function templates, take a long time to compile. So we need to get rid of some templates. And problem 4 is that we have pretty draconian arbitrary limits.
So really that you have so many template instantiations. You have a lot of constexpr code that has homogeneous constexpr, right?
Right. So the templates come from the fact that our JSON value is a template, and therefore all of our parse functions are templates instantiated every time for the level that we're parsing.
Because the tree itself, the size of the tree has to be known at compile time. So it's recursive template instantiations of all the tree.
But the depth of your tree is only 75 or whatever.
Yeah, but it still worked out. I mean, it was still a lot, and it was slow.
I mean,
I'm questioning the fact that it's caused by template instantiation. Actually, Chandler told me at some point that currently constexpr calculations work pretty slow, comparable to template instantiation.
Well, Ben fixes it. So
To clarify, each step of an evaluation of the constexpr function is much faster than a step of template instantiation.
okay.
The template instantiations can be memoized, which
Right.
can reduce the algorithmic complexity of a large computation.
yes.
So
So
nqueens is much more efficient in a template instantiation metaprogram, but like small steps are much faster in constexpr.
okay. So yes. So Chandler's point was that because templates are memoized, so templates constexpr is faster to evaluate individual steps, much faster than instantiating templates. But once you've instantiated a template, it's memoized, so your template version can beat the complexity of your.
But with this
constexpr.
tree, you're not instantiating the same thing twice.
Right.
So
Yes, because the non-type parameter has to decrease. All right. Anyway, these are significant problems, and the next thing was to try and get rid of these. So the problem is we have templates, and all these recursive templates are problematic. So I just made a parsing framework. So I'm like, what can I do with this? The solution is obviously more parsing. What we have now is giving the literal and parsing a JSON value out of it. What we can do is write another parser that runs over the literal and tells us the number of JSON values we're going to need. And if we know the number we're going to need, then we can right size an array, parse again into that array, and we can fix the templates. And writing a parser that returns the number of values is fairly easy compared to actually returning the values. All you do is say arrays are 1 plus their children, objects are 1 plus their children, everything else is 1. And you've already got all the kind of structural stuff you need to do to understand running over the JSON. So that's what I did. And then given the result of that, we can now take out, this is, before this was the function, this is the top level function template we had before. Well, now the template is up at the struct level. All the functions are just static constexpr functions. They're not templates. They don't need to be instantiated for every level of the tree. And we have right-sized our vector that we're going to parse into. So this required a slight change to the JSON value, which was that the vector and the map inside it no longer store values. What they store are offsets into the array of values that we've parsed. In particular, offsets from their own this, as it were. So this is what an example kind of parse ends up looking like in object layout. So simply we've got an array which contains 3 values, and one of the values is itself an array. So what we're going to get out in our, our number of values parser comes back with 6 because it's 2 arrays and 4 numbers. And then when we parse into our JSON value array, we get what you would expect. So we parse the outer array, and then its children are the first child goes into the next one. The next child is itself an array, so we recurse into that, and we get its children, and then finally we kind of pop out of that, and we get the third child at the top level. But we've right-sized the value array at this point. Thanks, Tony. It gets better. There's more to come. So this did require this template form of the literal, which I believe is a GNU extension right now.
Yes, but it should work with the regular.
I don't know enough about it. But
Well,
I do
according
know,
to the standard, it should work, but we couldn't get it to compile with any compiler. But this compiles.
This was proposal N3599 by Richard Smith. There's no reason we couldn't have it in the standard. The thing here is, like, to run the first parser, as soon as you get a parameters aren't constexpr. So you need to turn your function parameters into template parameters in order to be able, and you just expand them in an initializer list. And then you can call another template function which runs your numObjects parser here, return the value, and only then, because that was constexpr, you can use that as the template argument for your right-sized array. And what you end up producing here is the entire array of values, and the root value is index 0. So at the cost of an extra pass, I apologize for my accent, which sometimes confuses us. We don't get the recursive function templates anymore. And there is no arbitrarily hard-coded depth limit, which means we can do silly things in our tests. I just mashed the bracket until I had something, and then I guessed at the number of zeros. So we still have some arbitrary limits, though, on strings, arrays, and object sizes. So, hey, I've got a parsing framework. Let's use it. So we can use the exact same technique we use for values for strings. We can write a parser that pulls out the entire string size that we're going to use, the same way we pulled out the entire number size we're going to use. So we pre-compute that, right-size the character buffer in the same way we right-size the value buffer, and then our strings in our JSON values become effectively string views into the externalized string array of chars. So, and in fact, we can merge this in with a number of values parser because they're not altering anything. They're just parsing 2 values. When I did this, I did find out that structural bindings don't currently work constexpr. And so this is what that looks like. This time we have, very similar to before, kind of the array setup with the strings. Number of values is still 6. Total string size of all of the strings comes out as 14. We right-size the character buffer and we right-size our value buffer. And now our strings contain effectively string views into our externalized thing. So X here, and then this is the string view that covers all, etc., etc. So you can see that works exactly the same way. So now we're down to limits on array size and object size. And we can't naively do the same thing we did with strings because values within the children aren't necessarily contiguous, right? Because arrays can contain arrays or objects or anything in general. You can see here that the outer array, its children aren't contiguous. If they were contiguous, we could store offset plus extent. So to make them contiguous, we just need to turn a depth first parse, which is inherently depth first, into a breadth first parse. So, I mean, I had this idea, but normally the way we would do this is by using a queue or something like that, and anything like that would have to grow and we wouldn't know at compile time how to size it. But hey, we've got parsers, so let's use them. So, all we need to do is make a parser that parses out the unparsed string view that represents our child. And then we can effectively lazily parse that. So we extend our JSON value with one extra kind of field representing the uninitialized value, which is still the string view that's going to produce the value. And now when we have this, we can write a parser and this is kind of the intermediate stage. So when we're parsing this outer array, what we're going to do is parse its children into unparsed states, which are the string views that represent them. And then once we've done that, hey, our children are all contiguous now. We can go back and reparse them and just put them on the end. And so that's the kind of intermediate state. The unparsed children are obviously the values, the string views representing the values they will be. So arrays are now offset plus extent, no limit on array size. Similarly to arrays, we can do objects, because objects are fundamentally alternating keys and values. Keys are strings. We already know how to deal with externalizing strings, so just make object keys into values that happen to be strings, and everything's going to be happy. So this is an object, right? And it's an array, but it's an array of alternating values. So effectively, its children are contiguous. So yeah, alternating string and number and string and number. That's the result of parsing that. So now our JSON value, now that we have all this parsing framework which is doing what we want, our JSON value boils down to just this. The string and the array and the object have all become effectively views into our external storage, which is part of our constexpr object now. And this is kind of no limits. This is our final representation. This is, given all of our parsers, we can do this. So the conclusion to parsing is constexpr lambdas really enable this. Like, as soon as I heard about constexpr lambdas, I'm like, I think we can do this now. Parser combinators are the key to this. And the key is that when you combine parsers, what you get is another parser. So they're all composable and can be built up like this. The template user-defined literal stuff unlocks the ability to do multiple parses, in particular to do that initial parse where you right-size the value array and the string array. And adding extra parses can solve almost any problem, as I found out. So, you know, maybe a parser is a concept. I'm not sure. I don't know enough about concepts yet to really answer that question. But, you know, maybe this could have been helped by concepts. And that is the end of that section.
So, for the future, currently we have a problem with destructors. Any type with a non-trivial destructor cannot be used in a constexpr context. So we're going to have a little quiz. Is this trivially destructible? Is S trivially destructible? So let's raise hands. Anyone says yes? S is okay. Everyone agrees. Is S still trivially destructible? Everyone agrees.
Yes.
Is S still trivially destructible?
No.
Oh, I got half of it. Oh, one and a half hands. No, it can't be because unique pointer is not trivially destructible itself. So S cannot be trivially destructible. Is S trivially destructible now?
No.
I wish.
I wish was the answer from the crowd. So, yes, we have this problem. Why is this a problem? This is my example of why this is a problem. I've taken the concept of my constexpr-enabled container and said, well, what if we got past the end of our statically allocated array, in this case of 10? And so in our pushback, we say, well, length is greater than or equal to our size, and we have not yet allocated something. Let's allocate some more storage and just expand it at runtime. And this works. And if you were to use this in a runtime context and go beyond those 10s, it would work. And if you use it in a compile time context and go beyond 10, then you get a compile time error. It's exactly what you would want. But we have a problem. We can't add a destructor. So if we want to do this, we are required to leak memory. Required to leak memory. The compiler won't let us do anything else with it. So there are proposals to try and address this. We have a proposal that suggests that if the body of the destructor is empty, then it should still be allowed in a constexpr context. So by using if constexpr, we could create something with an empty destructor optionally. But there are other tricks to do this because, I meant to actually put a slide up in here and I never did. But
so you would basically write if constexpr with the constexpr operator.
that would be awesome. I didn't even consider that. If constexpr, if that first proposal that we talked about goes through, then we would have a way to actually determine constexpr con. That's brilliant.
Yeah.
But you could still accomplish the same thing, maybe, because there are tricks right now that some of the standard library things use that have to be trivially destructible if all of the things that they can contain, like variant, is trivially destructible if all the things that it can contain are trivially destructible. And you can do that by conditionally inheriting from a base class that is trivially destructible. So using your trick, we wouldn't even need this. If we get, we might be able to do the same thing if we have the constexpr operator.
But all the boilerplate for that base class is awful everywhere.
The boilerplate for the base class is awful. I played with it. It wasn't horrible. It was.
Did you see how it looks in, say, libc++?
No, I played with my own implementation, not with what the standard library ones do.
Go check out the actual implementation in libc++.
Okay.
It's not pretty.
I think
That's why we
you.
buried it in the standard library.
I know.
I was going to say you might have offended someone here with that saying it's not pretty. I personally think that a destructor should be treated like anything else. If you don't call code that is not allowed in a constexpr context in your destructor, then it's constexpr allowed. Like, why not? Yes.
So is that part of your proposal?
I have not actually created a proposal for this. I'm just saying these are possible solutions that I think would be interesting.
Is there anyone in the room that knows for sure why it was specifically ruled out of the list of things that can appear in a context expression?
Most of the answers to licensing in context seems to be because we didn't think about it.
Yeah.
But I think, so Bryce just said most of what he's heard is things aren't constexpr because they didn't think about it.
I would not assume that there was intention, that it was intentionally excluded. It is very possible that it was just that it's never been considered.
So it's possible it was just never considered that you might have a constexpr destructor allowed.
Or it might have been considered and somebody said, I need to go investigate it, and never did.
And it never had the investigation, yes.
And there are many, many, many things to be considered individually.
Yes, there are many things to be considered individually.
We're still just at the dawn of the third age of constexpr.
Yes.
So many things are unknown.
So we also have a debugging problem. I'm getting okay. So what line does GCC report an error on? Who wants to throw answers out?
6.
No, it's not 6.
Internal compiler error.
No, I got very few ICEs, I think, on this project.
Yeah, no, I didn't get that many.
Yeah. But when you're working with nightly builds of bleeding edge compilers, I think you can expect it to some extent. So the answer is you get the error on 9 on the actual constexpr invocation,
Right.
but that doesn't tell you what went wrong, right? Like it just says you accessed past the end of an array. If this is a trivial example, when you're talking about building up these strata structures that we were playing with, it wasn't obvious.
Yeah. Can we agree that 4 would be a good choice?
Yes.
Yeah.
And for the record, Clang does actually give you the trace in this case and tell you where the error happened, but GCC does not. So, did I just skip a slide?
Nope,
No, sorry.
you're
Okay. Personally, for me, several times while debugging, I had to actually take the examples for the data structures out of compile time context per context, put it intentionally into a runtime context so that I could hop into the debugger to see what I was doing wrong. And you have a different story that you'll get to, I guess.
Yeah.
Unless you
Well,
want
my story was I didn't so much have to take things out of. I was mostly working. I had to go back and make sure the types lined up in all the lambdas I was composing. It was mostly a case of scaling it back to simpler stuff and building up and figuring out where I'd gone wrong.
So the same person who proposed the constexpr operator has also proposed constexpr trace and constexpr assert, which will give us the ability to actually, instead of having to do some static assert kind of
Right. Or
trick,
throw a string.
or throw something, you could actually put a message in here and get a reason why something got invoked that you didn't expect it to. And then there's another proposal also, and I don't know who this person is. Does anyone know him?
He's pretty
David
awesome.
van der Voorde. He's the author of C++ templates.
Oh.
Back in the day.
We should probably make sure that you meet him this time.
Okay, I need to meet him. Oh, are you? No.
Come to Toronto.
It's not. No, that's
Come.
not.
I'm like, that's Odin. That's not David. I'm sure of this.
A comment on the previous slide, that would allow you to express errors in templates when you have exceptions off, because that's a big problem.
Oh, okay.
Right.
So
Yeah.
and this would allow you to express errors in templates when exceptions are turned off, you said?
Yeah.
Okay. And yes, you had a question?
And instead of conceptual vector proposal, we have already a proposal for contextual allocator.
Oh, there's already a proposal for constexpr allocator.
Yeah.
I don't know about that one. What?
But yeah, the constexpr trace would be, I'm sure, widely usable.
This is the best thing ever.
So constexpr vector is a vector that can grow at compile time. It requires compiler support. And it could have basically eliminated a lot of the stuff that you had to do with right-sizing everything.
Sure.
Maybe?
Could. Quite possibly.
Possibly.
Yeah. While we're on the topic, a constexpr random device would be very useful for cryptographic string hashing.
It is currently possible to generate random numbers at compile time.
Constexpr F string.
Constexpr F string.
I don't know that one.
No.
I'm only half
Yeah.
joking.
Oh,
So,
okay.
so yes, you can write constexpr random number stuff. The
Yes.
problem is you don't have a great deal of what's it called, entropy
Yeah.
available at compile time.
The best
You're
I've
very
come up
limited.
with is using date and time macros. But you can, and it works. So why not? Why not a random device?
I mean, the deviant people will hate you for the reproducible builds project on this.
Well, we're not so concerned about reproducible builds when we're doing experimental fun talks in Nashville.
You can always just return 9.
Yes.
Yeah.
999, yes. It's no way to know if it's random or not. So we're running low on time. I'm gonna
Do you think that is one thing that should be a macro?
a random number.
Yeah.
Yeah, why
so that
not?
you can set it from the compile time line. I mean, the compiler line, and
That would
get
make
the
more sense than
reproducible
random
build.
device. Yeah. I would be okay with that, but I don't,
Underscore random seed underscore.
Yeah, underscore
Sure.
underscore random seed. Why not?
Some way to get entropy from the compiler, which it can do.
I mean,
I
just
assume.
dash d it on the compile line.
Just have to convince Chandler to add it for us and
You can
see if he's paying attention.
include def random or something.
Include dev random. Yeah. Would that work? I wonder.
That wouldn't terminate.
Yeah, it wouldn't terminate. That's what I'm
Well, if
thinking.
you pipe them down,
Okay, so currently the only 3 algorithms that we are aware of that could not be made constexpr with their current requirements are stable cert, in-place merge, and stable partition, right? Because they all allowed to allocate temporary buffers.
Right. But we
optionally allocate.
well,
Yes, they're allowed to is the thing.
They should, to be efficient, I think is the point.
Yeah.
We know how to do these algorithms without allocating.
Right.
And so we could, or actually, I think they are required to allocate the buffers in order to meet the complexity guarantees which are required. I think maybe that's the case. No? Okay.
No, the spec says that they are of n if memory is available.
If memory is available,
Oh,
right.
that's true.
Oh, so you could just say if operator constexpr,
Yes.
memory's not available.
Yes.
And reduce the,
Okay. So these could be made context where we know how to do it.
Go forth and implement.
Stable partition, in-place merge.
I think that is
Yeah,
Okay.
those are the three that,
Stable sort.
that
Yeah, stable
stable
sort,
sort.
in place merge, and stable partition, yeah.
I'm looking.
Oh.
Marshall's checking this up.
Yeah, we've got 5 minutes. All right. So,
You guys can go over. The food's not going to be ready at the picnic. Don't worry about that.
I'll be hungry though. Is the problem.
Food won't be available.
Okay.
I gotta go out and cook it.
Yeah, some of us have to go cook, so.
Oh, Marshall, you're allowed to leave.
So we
want to
made
hear the end.
we made these constexpr containers, and we see no reason why many iterators, if they're working with constexpr containers, shouldn't be basically all constexpr.
Yeah, so, but there's only a little like pieces. Like standard next is supposed to be constexpr, but an implementation
And
problem.
distance is a
And
similar
distance,
story.
yeah. But why not back insert iterator? My vector has a pushback.
That's
There's no reason it could
constexpr,
work,
yeah.
but the standard doesn't currently. So, yeah, then I'll write all this up after we're done and submit a proposal. Okay.
You should do that, so you have to come to Toronto, say, to meet David.
When is Toronto?
July.
July.
Right after 4th of July.
Oh, that's not going to be possible
And
for me.
Albuquerque in November.
That's also that's not possible on the other end for me. I'm hoping to be at another conference then. So cost. To me, the flat data structures that we were talking about were easy to reason about. Constexpr code, I think, forces you to consider what your code is doing in the lifetime of objects in a good way. And in fact,
I would say.
for me personally, after working on this, now everything that I write, I'm like, I start with constexpr in front of the function, and then decide if I can't make it constexpr.
Yeah.
I think that building these tree-like data structures was difficult to reason about.
Well,
He didn't think that it was hard.
mean, tree-like data structures, maybe yes. Tree-like evolution of processes in a recursive way, that's a little easier to reason about sometimes, because you can just sort of assume magic happens in a recursive case, and then it works.
proof by induction, and it's done.
You just have
Yes.
to embrace induction.
Right.
Is constexpr another default that is wrong?
Could
I think I've been told to not be negative about these things. I'm sorry. The question was, is constexpr a default that's wrong? I've been bad about repeating some of the comments. Yes. So I think maybe, and no except maybe too on the other end. So error messages. What did you say? You had an anecdote about your error messages?
I had to, I was running my compiles from within Emacs. Frequently I had to kill the compile because a single line of the compiler's output was going to be megabytes in size, and it was just slowing down the editor. So when you have lambdas and containing lambdas, it builds up a bit. So yeah, my approach to debugging was just look at the code some more and figure out where I went wrong. I couldn't really use error messages. Go back and think about the types. That was it.
Yeah. So, cost of building a debug build. So everyone wants to know compile time cost. 6 gigs of RAM. So there's a little bit of I'll get into the disconnect here in a second. More than 2 minutes for our simplest test cases, and produced a 338K binary. But tweaking the debug level had some effect on this. And so and going to the next slide, I was communicating with Ben saying, how are you compiling this? It's taking me minutes. I'm running out of RAM. My VM isn't big enough. And he said, I don't know what you're talking about. It takes, 5 seconds to build for me. And it turned out I was doing debug builds and he was doing release builds. And
you see, that's the great thing about constexpr. There's nothing to debug. If it builds, it works.
So we think must be something related to shuffling around debugging symbols and that kind of thing in the compiler that we don't know enough about. I certainly don't know enough about. 9K, it's so the release stuff is spot on. So
this is a much better story. I hope you agree.
It's yes. So this is a complete program using the same nightly build of GCC. How long does this take to compile? You want to take guesses? Either. I have numbers up for both as soon as I click next.
6 seconds.
6 seconds? Yeah, that's about right. So 5 seconds for the debug, 7.5 seconds for release. I mean, so the stuff that Ben did is, it's, why not? It's totally usable.
Fun.
Yeah.
I mean,
if you don't care about debug builds.
Right. But like I say, there's nothing to debug.
There's no right.
It's all compile time.
What about the memory usage?
Excuse me?
What about the memory usage?
I don't recall on this slide, I'm sorry, and I didn't write the number down. So
in conclusion.
Yes. All but 3 standard algorithms can easily be made constexpr, we believe.
There are a few holes in the STL, mostly around assignment operators, some of which could be overcome.
I hope you have a list.
Well, this is most of the list. We can make it, yes. But the problem is I think I have to roll it into other stuff that I've been looking at. So.
Doesn't have to be today.
Okay.
By tomorrow.
By tomorrow, we'll have a list. Yeah, all right.
All the time we're working on this, Jason's like, I want to put this in C++ weekly.
Yes.
Lots of grist.
Yes, I was restraining myself. There's lots of things I wanted to show and other examples. What's this? Oh, iterator operations. Yeah, right.
Constexpr iterators.
I have a concern that what's that?
There are LWG issues about that.
About CMath?
No, about iterator operations.
Oh, okay.
There were open LWG issues about that.
Oh, okay.
CMath is harder. I filed the national body comment for this.
Yes, so I think that this might hold us back on some constexpr things, and Bryce is agreeing because of the interaction with math.h and CMath.
Yeah.
Can we make things constexpr that C wouldn't understand what that means? And
It depends how much you want your
okay.
We've generated a lot of work.
Yes.
They have to be the same. So the things in CMath, my understanding is that they need to be the same functions, the same addresses.
Same functions.
So like if you need to have forwarding, like
so why not CX math?
That's not good.
Yes, why not have a CX math? Or if the internal implementation of the oh no, because you still have to put it on the signature.
I think CX math probably fine, but like the ones that are actually in CMath probably can't.
Why do we have that on CMath and not most everything else?
It's any of the stuff that has to be any of the stuff we import from C.
Any of the stuff that we import from C might have a problem. I'm going to keep clicking.
Well, some of the stuff we import from C already has like underscore throw on it.
Oh, that's interesting.
So we could like have like underscore constexpr.
Oh, all right. So we're let's try to wrap this up. We've only got like 2 clicks left. All right. So
constexpr lambdas. They can do everything.
I think constexpr allocators are possible. Apparently, there's a proposal for that. And I think it should be doable with enough work that we could actually unify our containers and say, well, I want something with a statically sized constexpr thing, and it's a standard vector, and have it do what we expect to do. I think that should be possible.
Mm-hmm. So thank you very much. And that's the GitHub.
And now Marshall gets to go cook.
We may have a few lingering questions.
Yes, we can.
I don't know if we have time to take them.
Yeah.
But no, I'm very serious about this. I would love to see the problems you ran into.
Yeah, we need to put it all together.
Both standards problems and library implementation problems.
Okay.
Don't worry, Marshall, I'm not going to want to leave this week without getting something done.
Okay. So yeah.
In the back.
Just a quick comment. One of the reasons why the community has been more conservative about adding constexpr is because adding constexpr to stood invoke broke and changed the semantics because it triggered some early instantiation of templates and stuff like that.
Okay.
Just a comment to be mindful of that.
Right. So yeah. So the comment is it's as well to be careful about adding constexpr. Adding constexpr to stood invoke broke and changed semantics. So we're a bit careful about that sort of thing.
Yeah. Sorry.
Yeah.
We can't both be pointing at people. I'll just.
This would be completely wrong because it's not my domain, but might the reason that you can't make every standard swap constexpr be because of polymorphic allocators in the things that you're swapping?
Okay. Just marking a function constexpr doesn't mean that everything that is invoked by it would be usable in a constexpr context. I'm almost positive we just need that constexpr keyword on the front of swap, and if you try to use it with a type that can't be done in a constexpr context, then you would get a compile time error. Otherwise, it would just work.
Yeah.
Right.
I think I get agreement. Yes, Juan.
So I suspect that maybe you could like decrease the compile time a lot if you removed the sizes from the types. And I was wondering if you could get away by having something like an arena allocator for where you basically in your vectors and everything you just pull memory for it, and you could like looking at how your parser works. I was wondering like most probably you can find like a constant factor of the input stream that will give you always enough memory to actually.
Well, that's effectively what Ben did. He pre-allocated all the storage and then indexed into it.
But you were still like
I was still
sorry.
Right. Yes. I mean, it would be possible. I mean, my first thought was, let's just make a big buffer and go into it. But then I thought, I'm not satisfied with having all that slack. I want something that's right sized.
Yeah.
But yeah, I mean.
What I see is like the problem.
I mean,
is that
we're all C++ programmers, right?
Like you are reinstantiating, I think, a lot of the parsing functions for the
True.
sizes of the things. So I mean, it's just like an optimization and anything. I admit like. It's much more elegant, I think, the way you did it from a type point of view.
Well, yeah, like I say, our first cut was the simplest thing that worked, and it was pretty bad. This is only the second cut, right? There's a lot more that can be done, I'm sure.
Yeah.
Zach?
Yeah, I just want to point out that there's a real fear in LEWG that adding constexpr or no accept to stuff that to types for which is not part of the fundamental design that they have those is constraining implementations who want to experiment with these things or introducing possible problems like stood invoke. And so the idea is don't tell implementers they can't add it, and don't add it now unless it's part of the design of that type that it needs it. That's kind of what people are feeling in LEWG these days.
So the comment was you don't want to overly constrain the standard requirements by saying constexpr on things that we don't know the full implications of effectively.
Well, the feeling is that we don't, as a community, have a real great grasp on what best practices are yet.
Right.
These new features. So.
But and constexpr is a lot of times types are born intended to be constexpr, and so adding constexpr speculatively elsewhere is something we need to be careful about.
But I find like the one that really stands out to me is standard pair. Not like every aspect of it is constexpr except the assignment operator. So you can do, pair dot first and assign it, pair dot second and assign it and get the same effect. I feel like that should be considered a defect that we can submit in a proposal or something. With these trivial types, definitely, yes.
And I may, Louis, you may need to clarify this for me. So my understanding is there's one place in C++ 17 where we can have a function, that is constexpr without being marked, and that's a land-based call operator. The constexpr is optional. You don't have to put it.
Right.
So
that's right.
Really, this idea of trying to figure out lists of all the things that we should make constexpr. I would prefer that we try to figure out more ways that we can make things that the compiler can determine a constexpr, just be constexpr out of the box.
That is way outside of my knowledge. Yeah. We probably really should wrap up, I think.
One more then. Let's do it. Well, Vittorio just put his hand up right before you said
Yeah,
that.
sorry.
Are you done, Bryce?
Yeah.
So there has been like some discussion on Slack about a possible way of passing constexpr parameters by wrapping stuff inside a lambda, which is included in constexpr, and passing the lambda and then calling it from the function. And that guarantees that what you're getting out of the lambda is constexpr. So that's a way you can do constexpr.
Does that work currently?
Yeah, there are some examples. I haven't explored
okay.
it yet, but it's
So,
promising.
The classic example
from Vittorio,
of adding a layer of an integration.
from Vittorio to the world, if you want constexpr function parameters, wrap them inside lambdas, which are then constexpr callable. You can get them out.
I feel like there's another Dr. Seuss thing in there about lambdas of parameters of.
All right. Thank you all.